So I'm Naomi, and I'm in my third year with Stuart Lyon, doing the thermal agent and degradation of epoxy coatings at oxidised interfaces. So my project's focused on corrosion under insulation. So it's the coating is applied to a carbon steel pipe, and then that's coated in insulation and then coated in a metal jacket. But sometimes this metal jacket can become damaged and allow water to ingress, and also salt solutions or corrosive material which can degrade the coating. The coating also goes through cycles of 50 to 175 degrees, and this can also lead to humidity cycling. And so the coating degrades, as you can see here. This is pictures from AXO, where the temperatures change the coating's colour and has also caused the panel to bend. We know that it starts to oxidise at 105 and there's colour changes. So my project aim is to determine the breakdown mechanism and to determine the influence of the parts of the formulation, including the role of pigments. So to do that, I'm going to age my coating and have a look at the cross sections using AFMIR and other methods. So my first initial experiment was to have a selection of coatings, all with 5% pigments, but the pigments were all different. So I had aluminium flakes, two different iron oxides that were meant to be different in size, but turned out to be chemistry as well. And I aged them in 4 different ways. So I aged them in an oxygen oven at 175 degrees, in a vacuum oven at 175 degrees, but I purged it with nitrogen, and AXO aged it at their site in a humidity chamber at 60 degrees at 100% relative humidity. They were all at 30 days, and then I did a milder aging scenario at 105 degrees C. Sorry, I should also mention all my coatings were post-cured, so they had a T0 made for them, and they were put in the nitrogen oven at 100 degrees for 2 days. So I did glass transition temperature measurements on them all, and I found out that the non-pigmented had a significantly lower TG than all the pigmented. The differences with the pigmented weren't significant enough to make comparisons, really. I'm sorry about the micaceous iron oxide, I just didn't have that sample, so that's why that's not applicable. So in the next few slides I'm going to be talking about the bottom and the top surface, so I thought I'd explain how I access them. But this coating is 100 microns thick, so I'm able to peel it actually away from the carbon steel and look at both interfaces quite easily. So something I can do at Manchester is nanothermal analysis. So it's here. So I created a height map with the AFM to look at my surface. This is the bottom surface actually, and then my cantilever tip heats the sample, and as the sample expands, the deflection is measured, and then when the polymer softens and the tip sinks, the deflection decreases, and that's the transition point that's measured. So I looked at my bottom surface in my post-cure sample and tried to distinguish a softening temperature. For the raw data, I got around 100 to 130 is where you can see the general transitions. These are all failed samples, I think, because there's trapped solvent at the bottom of the coating. So this was the 105 age. As you can see at the bottom, more of the sample was able to run successfully, and I got softening temperatures between 118 and 138. When I looked at the top surface, the softening temperatures increased, and also, just as another note, is the topography was different. It's much smoother on the top surface compared to the bottom surface. Same with the post-cure sample. I got much more stable transitions and was able to look at them. I'll come back to this, but I want to do a quick explanation of what I did next. So at AXO, they have this facility where you can do headspace GCMS. So you can have your paint sample and it can be heated in an oven, and the released volatiles can be put through a GCMS column and then go through the MS analysis, and you can work out your solvents present in your coating. So AXO provided me with that list, but it just to name two, I got xylene and butanol, and I found solvents were all present in all my samples, and the technique heated them only for 30 minutes at 105 degrees C, which is standard. So that was important, because when I took out the raw data for the nano TA, some of the transitions were actually just boiling points for these solvents. So I removed that from my data and tried to work out a different softening temperature that didn't have the solvents included, or the known solvents from the headspace analysis. So I have the top surface here for the 105 aged and the bottom surface here in orange, and you can see that there's a difference here between, the top surface has a higher softening temperature than the bottom surface for the 105 for a week. So when I did the top and bottom for the post-cure sample, my top surface had quite a small box and whisker diagram with the quartiles in them, and it was more consistent, closer to my actual measured TG when I did DSC. For my bottom surface, I had a wide range, even though I'd taken away the known solvents. But actually what I think happened here is this section of my nano TA was me degrading my sample. It seems like the solvents are encouraging the degradation of the coating, and the solvents are mostly trapped at the bottom. So I'm getting my polymer to degrade. So instead of having this box and whisker diagram for the bottom surface, when I remove those 170, it is actually lower as expected. I need to do more tests, but I think that that's the reason why it's degrading, is because of the solvents present. So based on those results, I have the top surface has a higher softening temperature than the bottom surface, and aging the coatings increases the softening temperatures. A lot of the regions of the bottom surface are too plasticized to generate consistent TA data, and the results suggest that the solvents present are degrading the polymer or increasing the rate. Just as a side note, is I did some FTIR on the top and bottom surface, and you can see that there's chemical differences here. So I have an amide present on my aluminium flake, just post-cure sample, but only present on the top, and that's not there on the bottom. So there are also chemistry differences, and that's thought to be due to diffusion limited oxidation, and only the top surface is oxidized. So my theories are that the coating contains solvent, which is causing a phase separation, as in what I'm showing here. So I've got fully cured, and then I've got a plasticized network where the trapped solvent cannot escape. Pigments are allowing the solvent to escape by creating bigger pore sizes, and it's being less plasticized. That's why it's got a higher TG. And then the differences between the pigmented and the non-pigmented is more about shape rather than chemistry. So in the future, I need to age the samples again, but at milder temperatures, and determine what the role of oxygen is, and see if this still occurs when I use the nitrogen oven. And I also want to do in situ FTIR, so I can track the oxidation bands being formed. I also want to do nano TA on the whole cross-section and determine where the softening occurs, and if it changes depending on the aging conditions. And that's everything. Thank you.
Thank you very much. We're open for questions.
Do you have any idea what the influence of adhesion on the steel is? Because you started on the steel substrate and then removed the coating, right?
Yeah.
So do you have any idea what adhesion will do also with the bottom part of your samples?
So the reason I could do this was because the adhesion was so poor, so I was able to pull it off. I still need to do pull off adhesion tests. I don't. No, so it wasn't stuck to the panel very well. So the solvents hadn't weren't. It wasn't because it was trapped to the metal that the reason the solvent was there, because the humidity chamber samples, it was it was so easy to peel off. They just aren't adhered well. When I look at them under the microscope, you can see that it's peeling off even when they've not been aged that long. But these are not fully formulated, just to clarify. So yeah, the adhesion probably isn't what you get in service.
I just have to say, these are not service coatings.
Yeah.
So it is designed to degrade quickly and designed to magnify the effects you expect to get, rather than this is actually what really happens on chemical plants. It's really important to You could also say that if there's no adhesion, it doesn't matter because the whole thing's wrapped with insulation anyway. But who knows?
Should have this on your first slide. This is not a surface coating.
Oh yeah, sorry. Next time.
Any further question? Yeah. Okay, then thank you very much.